Hello everyone. So through this video, I will be presenting to you my report, which is all about interference in thin films. So if you happen to see a thin layer of oil floating on water, bright bands on a soap bubble, or the blue-colored wings of a morpho butterfly, so these are just some of the many ways thin film interference can occur in nature. So there are a lot more applications of thin film interference. But how is it possible? So we have here a figure. So light shining on the upper surface of a thin film with thickness T is partly reflected at the upper surface. So we have path A, B, and C. Light transmitted through the upper surface is partly reflected at the lower surface, so the path A, B, D, E to F. And the two reflected waves come together at point P on the retina of the eye. So furthermore, the reflected light waves may interfere constructively or destructively depending on the phase relationship. So phase relationship is discussed by the previous reporter, and interference will differ if the waves are in phase or out of phase after they've been reflected on the thin film. The differences in wavelength among colors result into constructive interference for some and destructive for others. Variations in the thickness of the film causes the complexity in shapes of the colored rings. Thin film interference and phase shifts during reflection. So we have here a figure of the interference between light waves reflected from the two sides of an air wedge separating two glass plates. So take note that the angle and thickness of the wedge are exaggerated for clarity. According to our statements a while ago, we should expect that the path difference between the two waves is just twice the thickness T of the air wedge at each point. So this one. At points where 2T is an integer number of wavelengths, we expect to see constructive interference and a bright area. So we always see a bright area if we mean constructive interference. Where it is a half integer number of wavelengths, we expect to see destructive interference and a dark area. Along the line where the plates are in contact, there is practically no path difference and we expect a bright area. So let's take note of these statements and compare it to our um, results later on. So this is not the case. So let's discuss further to understand more about it. Light and dark fringes appear but are interchanged. Dark fringe found along the line where the plates are in contact. So dark fringe are found here along the line where the plates are in contact. Suppose a light wave with electric field amplitude E sub I is traveling in an optical material with index of refraction N sub A. It strikes at normal incidence an interference with another optical material with index N sub B. So the amplitude E sub R of the wave reflected from the interface is proportional to the amplitude E sub I of the incident wave and is given by this equation. E sub R, or the reflected wave amplitude equals n sub a, or the index of refraction of the first optical material, minus n sub b, or index of refraction of the second optical material, over n sub a plus n sub b times E sub I, or the amplitude of the incident wave. Okay? So we have here three figures on electromagnetic waves propagating in optical materials. Let's take note of our equation earlier, which is this one on the bottom, in the bottom part. So in figure A, so as what we can see, n sub A is greater than n sub B, meaning light travels more slowly in the first material than in the second material. So in this case, E sub R and E sub I have the same sign, and the phase shift of the reflected wave relative to the incident wave is equal to 0. So in the second figure, as what we can see, n sub A is equal to n sub B. So the amplitude E sub R of the reflected wave is 0. So the incident light wave can't see the interface, and there is no reflected wave. So in the last figure, n sub A is less than n sub B, and light travels more slowly in the second material than in the first. So in this case, E sub R and E sub I have opposite signs, and the phase shift of the reflected wave relative to the incident wave is pi rad, or which is equal to 180 degrees, or a half cycle. So 180 degrees is a half cycle um, phase shift. This is analogous to reflection with inversion of a transverse mechanical wave on a light rope at a point where it is tied to a heavier rope or a rigid support. So that's when we talk of mechanical waves traveling on ropes. So, according to that, to what we discussed a while ago, for the wave reflected from the upper surface of the air wedge, n sub A, or the glass, is greater than n sub B, or the air. So this wave has zero phase shift, so the one on the red. For the wave reflected from the lower surface, n sub A, or air, is less than n sub B, or glass. So take a look at the one on green. So this wave has a half cycle phase shift. Waves that are reflected from the line of contact have no path difference to give additional phase shifts, and they interfere destructively. So here is our mathematical summary. In the film, if the film has thickness T, the light is at normal incidence and has wavelength lambda in the film. If neither or both of the reflected waves from the two surfaces have a half-cycle reflection phase shift, the conditions for constructive and destructive interference are 2t equals m lambda, where m is an integer number of wavelengths, or is equal to 0, 1, and 2. By the way, m here stands for the number of fringes. Okay? So this is the condition for constructive reflection from thin film, which has no relative phase shift. And 2t equals quantity m plus 1/2 lambda, where m equals integer number of wavelengths, is a condition for destructive reflection from thin film with no relative phase shift. So this is applicable for interference which occur, for example, on soap bubbles and the like. So on simple cases lang siya. But if one of the two waves has a half-cycle reflection phase shift, the conditions for constructive and destructive interference are reversed. So we now have 2t equals m plus 1/2 lambda as a condition for constructive reflection from thin film with a half-cycle relative phase shift. And 2t is equal to m lambda as a condition for destructive reflection from thin film with a half-cycle relative phase shift. So these reversed or new equations are the conditions for interference which involves an air wedge, just like what we discussed a while ago. So now let's go to thin and thick films. So thin films. The sun and light bulbs emit light in a stream of short bursts, each of which is only a few micrometers long. If light reflects from the two surfaces of a thin film, the two reflected waves are part of the same burst. Hence, these waves are coherent and interference occurs as we have described. So this light is coming from a single burst, and when it strikes a thin film, these reflected waves are still part of the same burst and are coherent. So this is what happens on thin films. How about on thick films? So if the film is too thick, the two reflected waves will belong to different bursts. There is no definite phase relationship between different light bursts, so the two waves are incoherent and there is no fixed interference pattern. So, which is why we only see colorful fringes on thin films and can rarely see them on thick films because the waves reflected from the two surfaces are from different bursts and are not coherent because the film is too thick. Okay, so we have here a sample problem. Please take a look first at the figure. So we have here our lambda naught for our incident wave, which is 500 nanometers, and the thickness of the air wedge T, also the length of the air wedge, which is 10 centimeters, and the height of uh, the end part of our air wedge, which is 0.02 millimeters. So what is the spacing of the interference fringes seen by reflection? So because it is an air wedge, so it is understood that it is the other wave or the wave reflected at the bottom surface is a half cycle out of phase. So we'll use this equation for destructive interference, which is 2t equals m lambda naught. So in here we are dealing with a triangle or a right triangle. So tan theta is equal to opposite over adjacent, which is equal to t, the opposite side, which is t, and the adjacent side, which is x. So this is our x. So this also is equal to h over L. So here H and L, okay? So let's substitute what we've got here. So we will have 2xh over L equals m lambda naught. So we just substituted our value for t, which is t equals xh over L. Understood? Next, from this, we can derive the equation and get this one, 2xh is equal to Lm lambda naught. So this becomes 2xh over 2h equals Lm lambda naught over 2h. So x equals m L lambda naught over 2h. X equals m, so let's substitute our values for L, which is equal to 0.100 meters times 500 times 10 raised to negative 9 meters. So that's our lambda naught. So we just converted our values into meters so that it will be easier for us to solve. So over 2 times 0.02 times 10 raised to negative 3 meters. So simplifying further, we'll have x equals m times 1.25 times 10 raised to negative 3 meters. So x equals m times 1.25 millimeters. So this will be the spacing of the interference fringes seen by reflection. So fringes will be spaced by m times 1.25 millimeters. So let's go now to Newton's rings. So what are Newton's rings? So a convex surface of a lens in contact with a plain glass plate. A thin film of air is formed between the two surfaces. When you view the setup with monochromatic light, you see circular interference fringes. The principle is often used in testing the uniformity of a polished surface by studying the interference pattern the surface makes when placed in contact with a perfectly flat glass surface. So again, this is just exaggerated to make it clear for everyone, okay? So each one indicates an additional distance between the specimen and the master of 1/2 wavelength. So these fringes indicates a distance from the specimen. So this lens is the specimen or the one being tested, and this perfectly flat glass plate here is called the master. So each fringe here indicates a distance of 1/2 wavelength from the specimen to the master, or between the specimen and the master. At 10 lines from the center spot, the distance between the two surfaces is 5 wavelengths, or about 0.003 millimeters. High-quality lenses are routinely ground with a precision of less than 1 wavelength. So one application is the surface of the primary mirror of the Hubble Space Telescope was ground to a precision of better than 1/50 wavelength. Unfortunately, it was ground to incorrect specifications, creating one of the most precise errors in the history of optical technology. Now let's go to non-reflective coatings. So light reflected from the first surface is a half cycle out of phase with light reflected from the second, and there is destructive interference. The thickness of the non-reflective coating can be a quarter wavelength for only one particular wavelength, so yellow-green portion of the spectrum. So this increases the net amount of light that is transmitted through the lens. This principle is used to minimize reflection from silicon photovoltaic solar cells. So this is an application of a non-reflective coating. By use of a thin surface layer of silicon monoxide with index of refraction equal to 1.45, this helps to increase the amount of light that actually reaches the solar cells. So the destructive interference occurs when the film is about 1/4 lambda thick. So here is our film. It's 1/4 lambda thick, and the light undergoes a phase change at both reflecting surface because uh, and, and or the index of refraction of the glass is greater than that of the film, and the index of refraction of the film is greater than that of the air. So here our N sub A is air and N sub B is glass or is film. So we have here a half cycle phase change. Also here, we also have here a half cycle phase change. Okay. Next is the reflective coating. So as what we can see here, the index of refraction of the film is greater than that of the glass. So what happens here is that there is a half cycle phase shift at the air film interface but none at the film glass interface, and reflections from the two sides of the film interfere constructively. By use of multiple layer coatings, it is possible to achieve nearly 100 transmission or reflection for particular wavelengths. Practical applications of these coatings are for color separation in television cameras and for infrared or heat reflectors in motion picture projectors, solar cells, and astronauts' visors. So, the difference between reflective coating and non-reflective coating is that non-reflective coating uh, allows light to a certain uh, wavelength of light to pass through uh, the, the film or our optical material, while reflective coating it allows for 100% transmission or reflection uh, of light of particular wavelengths. So let's now discuss the wings of a morpho butterfly. So actually, this is not a natural pigment, but the wings of a morpho butterfly is made up of microscopic scales with tiny ridges. So these regularly spaced flanges function as reflectors. They are spaced so that the reflections interfere constructively for blue light. So this allows the wings of a morpho butterfly to reflect 70% of the blue light that strikes it. So that's how amazing a morpho butterfly is. So that's how unique it is from other butterflies. So let's move on to our last subtopic, which is the Michelson interferometer. So this is how the Michelson interferometer looks like. So this is used by Michelson and Morley in 1887 in conducting their experiment. So the Michelson interferometer. So it uses a monochromatic light source and can be used for high precision measurements of wavelengths. So a device called beam splitter is used. Its original purpose was to detect motion of the Earth relative to a hypothetical ether, the supposed medium for electromagnetic waves. The ether has never been detected, and the concept has been abandoned. The speed of light is the same relative to all observers. This is part of the foundation of the special theory of relativity. So how it works? So we have here the first step. Monochromatic light is sent from light source A to beam splitter C. So from the source to the beam splitter. So rays 1 and 2 emerge from the beam splitter. So this is ray 1 and ray 2 going upside and travel towards mirrors M1 and M2 respectively. So this ray 1 will travel to mirror M1 and ray 2 will travel to mirror M2, which is a movable mirror. Next, ray 1 reflects off M1, passes through the compensator plate D, and reflects off the silvered surface P. Ray 2 reflects off M2 and passes through the beam splitter C. So this is our compensator plate D. So light from M1 will bounce back and pass through this compensator plate, which will again reflect to the surface P. So it is under our beam splitter C. Then these um, waves will merge. These final waves will merge going to the eye. So finally, the two rays combine and reach the observer's eye. If L1 equals L2 and M1 and M2 are exactly at right angles, the virtual image of M1 formed by reflection at the silvered surface of plate C coincides with mirror M2. If L1 is not equal to L2, the image of M1 is displaced slightly from M2. What is meant by L1 and L2 here is the distance between the beam splitter and the mirrors. Okay? If the mirrors are not exactly perpendicular, the image of M1 makes a slight angle with M2. When the mirror M2 and the virtual image of M1 play the same roles as the two surfaces of a wedge-shaped thin film, and light reflected from these surfaces forms the same sort of interference fringes. Suppose the angle between mirror M2 and the virtual image of M1 is just large enough that 5 or 6 vertical fringes are present in the field of view. If we now move the mirror M2 slowly, either backward or forward, a distance pi over 2, so the path length between rays 1 and 2 changes by lambda, and each fringe moves to the left or right a distance equal to the fringe spacing. If we observe the fringe positions through a telescope with a crosshair eyepiece and M fringes cross the crosshairs when we move the mirror a distance y, then y equals m lambda over 2, or lambda is equal to 2y over m. So if m is several thousand, the distance y is large enough that it can be measured with good accuracy, and we can obtain an accurate value for the wavelength. Alternatively, if the wavelength is known, a distance y can be measured by simply counting fringes when m2 is moved by this distance. In this way, distances that are comparable to a wavelength of light can be measured with relative ease. So we have here a sample problem. How far must the mirror M2 of the Michelson interferometer be moved so that 1,800 fringes of uh, helium neon laser light with a wavelength of 633 nanometer move across a line in the field of view? So we have our solution here. So given are the number of fringes m, which is 1,800 fringes, our lambda equals 633 nanometer or 0.000633 millimeters. So we have our formula y equals m lambda over 2. So y equals 1,800 times 0.000633 millimeters over 2. Y equals 0.570 millimeters. So this is how far the mirror M2 should be moved so that we can have 1,800 fringes shown in our Michelson interferometer. Okay, so this ends my report. Thank you so much for listening.